So somewhere in the history of math when they were first starting to solve this and somebody did graphically, some mathematician, I'm not sure who, recognized that we need a more accurate way than to solve systems graphically. Because one, as we mentioned, if your intersection point contains any kind of fraction, you're just going to be guessing at it. Well, is there a way to get around that? Could I graph it and still get to fractions? Yeah, I'd have to make a very precise graph though, wouldn't I? It'd have to be very large, and each little line would have to be like a fourth or an eighth, and that would be very cumbersome to do. So rather than do that, and, well, if your graph, like I said, if you didn't draw your lines very accurately and use a straight edge, you could be off. So another method that somebody came up with was, hey, we can substitute. Now, what does it mean to substitute? What are we talking about? Have we substituted this year? Yeah. We've substituted a lot, right? When we started the school year, we had some expressions like x plus 4, and then they said x equals 7. What does the expression equal? That's substitution. But instead of substituting numbers, which we will do eventually, we're going to substitute for a whole value. You know, what was our first method? We were graphing. And then I mentioned something like this. How would I simplify 2x plus 3 when x equals 4? I would substitute, right? I'd put in the 4 for x right there and get 2 times 4 plus 3. 8 plus 3 equals 11. So we can easily see that I can substitute a number in for a variable. Well, since we have two variables, if we could get rid of one of them, that would make our work much easier. And that's what we're looking to do today. We're going to solve that system by substituting in and to try and get rid of one variable. That is our goal. From these initial two equations, we want to get rid of one variable. And I'm going to show you what you look for. Okay. When you're doing substitution, what you want to look for is you want to look for, in one of the two equations, you want to look for one of the variables to have a coefficient of positive 1. That's the best coefficient to have. If you don't have that, negative 1 will work, but positive 1 is the best. If I look at those two equations, x minus 2y equals 3 and x plus y equals 6, do we have a coefficient of 1? Look at the bottom equation. Both x and y have a coefficient of 1. So that means I can rearrange that bottom equation to get one of the variables being equal to an expression, which I can then substitute into the top one. Like this. Which one do you want to solve for, x or y on the bottom? Y? You want to solve for y? That means I'm going to move x over here. Alright? That's a good choice. If it were me, I would have solved for y. I'll solve for x, because x has a coefficient of 1 up here. But we can go ahead and solve for y. So I subtract x from both sides. What happens over here? X cancels, right? And I'm left with y equals negative x plus 6. This is what y equals, right? Can I put this in the place of y up there then? Yes, because that's what y equals. Y equals this entire amount. So now I can take this entire amount and put it right there for y. And rewrite this equation to become x minus 2 times this whole quantity. This is why I put the parentheses around it, and just in case I'd have to distribute. Negative x plus 6 equals 3. The most common mistake made in substitution, students will forget the rest of the equation. So make sure you don't do that. Well, what do I have now? What have I just gained? I've just gained an equation with just one variable. If I have just one variable, can I solve for x now? If I know what x is, I can then solve for y. That's the whole point of substitution. Do you see why now I said that I just made graphing obsolete? Because now you can solve it just algebraically. You don't even need to graph. Alright, so first step, I'm going to distribute the negative 2. X. Negative 2 times negative x is positive 2x. Negative 2 times 6 is negative 12. Equals 3. Add my two like terms together here, right here. X plus 2x is 3x. Well, no. Can you combine x and a number? No. So what do I have to do? This is a two-step equation. What do I get rid of first? Add 12, right? Reverse order of operations. If I were going forward, I'd add and subtract last. Since we're reversing and solving for a variable, we do that first. We get rid of addition, subtraction first. That cancels. 3x equals 15. Divide by 3. X equals 5. Remember, you are looking for a coordinate. So your x coordinate is 5. So I can go ahead and put down the 5 right there automatically. Very good. Now I can solve for y by putting it in for x right there. Now, could I put it into one of these equations? Could I put that x value into one of those? Why wouldn't I? Why would I just plug it into that one that I rearranged? Yes, it's already solved for y, exactly. So I could put it in one of those top ones, but it's not going to do me any good. I will then have to rearrange everything to solve for y, which I've already done in that bottom one. So I'll put it in right there. And in this one, I get y equals -5 plus 6. Y equals 1. So my y coordinate is 1. So if I graph those two lines in the coordinate plane, they'd intersect at the coordinate 5, 1. What's the disadvantage of solving a system by substitution? Okay, define too much work. That's your definition. It is. It's a lot of steps. Okay. The way I'm going to show you tomorrow is better than this. And then when you next week when I'm out, I will show you the last way, which is it's the best. I think it's the least amount of work. So, but this way, some problems are naturally set up to be done by substitution. You'll see that. On your quiz and on your test, you'll be able to solve it using whatever method you want. There'll be some that'll be set up naturally to solve by substitution, but you could still use the other methods. All right. Let's do another one. Not if you don't want it to. Okay, let's solve this one by substitution. All right, I'm looking for a coefficient of 1 or -1. Which one has 1 or -1? The top or bottom? Bottom, right? Here, this y is -1, so I'm going to solve for y. So I do that by subtracting 2x from both sides. And I get -y equals -2x plus 1. Do I want -y? No. What do I want, Beth? Positive y, right? So I'm going to change the sign of everything. Just change the y to a positive y. -2x becomes positive 2x. That positive 1 becomes -1. Okay, now I can plug this in for y right there. So my equation now becomes 4x plus 3 times 2x minus 1 equals 27. Distribute the 3 here. 4x plus 6x minus 3 equals 27. Add your two like terms. Now, when you substitute, there are always going to be two like terms. Your variables, you're going to have to add them together because what was y is now an x. And there's another x there. So you will always have to do some adding of like terms. Always. When, Larry? Always, that's right. Yes? It does not matter if you solve for x or y. You'll still get the same answer, provided you don't make a mistake in your work. You'd still get the same answer either way. If we had enough time, I would show you I could solve for x in this one. You know, but yeah, I would have fractions. That's why we look for a coefficient of 1, because the work will be easier. Good question. Add 3 to both sides. 10x equals 30. Divide by 10. X equals 3. All right, now I'm going to plug in 3 right there for x. I can go ahead and mark that down as part of my coordinate. The x is 3. I just have to find my y. So I plug in for x right there. Y equals 2 times 3 minus 1. That's 6 minus 1. Y equals 5. There's my coordinate. 3, 5. Any questions so far? Will, does it look familiar? We did a lot of this last year in algebra. A lot. All right. These two. Which one which variable in which equation would I solve for first, or rearrange for? The first one up top, the x on the top, right? Because that has a coefficient of positive 1. So I'm going to rearrange this by adding 2y to both sides. When I do that, that 2y cancels, and I'm left with x on the left equals 2y plus 9. Am I ready to substitute now? Yep, I'm solved for y. I'm going to plug in for x right here. When I do that, I get negative 2 times the quantity, 2y plus 9, plus 4y equals 13. Distribute the negative 2. Have you noticed the consistent steps here? A lot of times after I substitute, my first step is to multiply, distribute. The only time that doesn't happen is if you substitute in for a variable whose coefficient is 1. Like if this were negative x or just x right here, I wouldn't have to distribute anything. Negative 2 times negative 2 is negative 4y minus 18 plus 4y equals 13. Now here's that step that we always have to do, right? We always have like terms. Here they are, my y's. Negative 4y plus positive 4y equals 0, right? So those cancel. And what am I left with here? Negative 18 equals, that's a problem, isn't it? Is there any variable left? Aha! I have a false answer. Negative 18 can never be negative 13. If you get a false answer, do you have an answer? No. So what kind of lines do I have with no answer? These are parallel lines. If you rearrange them and put them into slope-intercept form, they would both have a slope of negative 1/2. So these are parallel lines.
So if you get a false answer, they're always parallel?
Exactly. If you get a false answer when you substitute, you have parallel lines. Because y is not equal to anything and x won't be equal to anything. They'll never intersect. I could take those two, rearrange them, and you'll get same slope. So they're parallel. They cannot intersect. That is correct, sir. What's that, Marie? It's exactly the same thing. Are they parallel? They're not perpendicular. They're the same. It's the same equation. So what's going to happen? It's the same line graphed on top of itself. Where is it going to intersect? Everywhere. So you have how many solutions? A lot. Can you be a little more specific than a lot? An infinite number of solutions. Okay? Now, the book gets a little tricky on some of your problems. Let's say you didn't notice, obviously, that these two are exactly the same lines. They're going to intersect everywhere. They'll be graphed one on top of the other. Let's say you had something like this. Instead of this, you had 4x plus 2y equals 24. What did I do to this top equation? I multiplied everything by 2. Let's see what happens when you have the same line graphed on top of itself and it's solved. So if this were the original problem right here, I would solve for this y down here, correct? That's what I'd rearrange for. So I subtract 2x from both sides, and we just want to see what happens. Y equals negative 2x plus 12. So I'm going to substitute in this negative 2x plus 12 for the y right there. When I do that, I get 4x plus 2 times negative 2x plus 2 equals 24. Distribute. What's that? Oh, it's 12. Thank you. Remind me to give you your bonus points. All right, distribute the 2. That would make a big difference. Thank you, Kevin. Minus 4x plus 24. What happens to 4x and negative 4x? They cancel to 0, right? And what am I left with? 24 equals 24. It's always true, right? That means it intersects everywhere and you have an infinite number of solutions. So if you don't recognize that it's the same line to start, if you end up with two numbers that are equal, being equal to one another, a true statement at the end, you have an infinite number of solutions, infinite solutions, because it's the same line graphed on top of itself. All right. Bill and Chris, who were in my 7th period class last year, Bill and Chris Construction Company send 29 workers out in 2 crews. Yeah, you know, it's Machaca and Bill Ambrose. One crew has 5 more than twice the number of workers in the other crew. How many are in each crew? So, what are these equations going to look like? This is a system. There are 2 crews. They send 29 workers out in 2 crews. So our total is 29. This problem will require a lot of thinking on your part. So it has 2 construction crews, right? And 29 total in both crews. That means you have the number in the large crew, right? We're going to let that equal n. And then we'll let S be the number of workers in the small crew. So when you take the number of workers in the large crew plus the number of workers in the small crew, they have to equal 29 total. So now we need to come up with the other equation because it's equal, it's a system. Well, the other one's going to naturally just be already solved because what's the number, and that's the way they set up. One crew has 5 more than twice the number of workers in the other. So this larger crew has to be the larger crew, right? The large crew, n, has to be equal to 2 times the number of small workers plus 5. There's my system set up to substitute. So I'm going to substitute in for n right there. So I'll substitute this whole amount up top. 2s plus 5 plus s has to equal 29. Do I have anything to distribute here? No, I mentioned that. When the coefficient is 1, so what can I do with the parentheses? Get rid of it. 2s plus 5, or 2s plus 5, yeah. Plus s, my 5 and my s look the same, equal 29. Add my 2 like terms. 2s plus s is 3s plus 5 equals 29. Subtract 5. 2-step equation. 3s equals 24. Divide by 3. S equals 8. So the small crew has 8, which means the large crew has 2 times 8 plus 5, 21. So small crew 8, large crew 21. That's on pages 346 and 347. No graphing.